Thank you very much. My name is Seong Jin from National Tsinghua University. Today I'm going to talk about cosmic star formation history based on the JWST data. So this work was done with our group members here and it's published in the NNRAS. So yeah, the question about how galaxies have evolved and how they have formed the stars. This kind of questions have been one of the hottest issues in modern astronomy. So, how to constrain the models which can describe cosmic star formation history? This is one of the most important questions we have today. So, we already know the model plot, which tells us that the star formation activity in the universe peaked around redshift 2 and then decreased afterwards. But how about in the higher redshift? So, for example, in this figure, the higher redshift towards the ionization era, we see that there is quite large uncertainty here, as many different works shows different star formation efficiency. So, yeah, to find the answer to this kind of questions, we need to see the distant galaxies in the early universe. But our current observations have been mostly relying on the optical bands, which are strongly affected by dust obscuration. So we need infrared telescope. So we are using JWST because this is the most advanced telescope ever, which is optimized for the infrared observations. So the resolution is much better than the previous telescope. And if you see the right panel, you can see that the dust obscuration is much more serious in the optical bands. So this is why we need infrared observations. And it also explains, to learn more about the star formation activity and star formation history, it is essential to understand the infrared galaxies, which have a large amount of dust. Because newly forming stars are surrounded by dust like this, so which means the critical phase of a star formation is taking place in this kind of dusty and dust-obscured environments. So our method on how to construct the cosmic star formation history model begins with the infrared source count. So cosmic star formation history is usually presented in terms of star formation rate density. And this is usually derived from the luminosity function, which is defined as a number of galaxies in a specific volume as a function of luminosity, which provides important information about galaxy population and their evolution. And source count is closely related to the luminosity function. So when we have data, it is we can easily obtain the source count results because it's really easy. But this is just a number count of the sources projected on the plane, kind of a two-dimensional surface on the sky. So there is no redshift information. But to construct star formation history as a function of cosmic time, we need a redshift. But in many cases, normally we don't have. So we may be able to study evolution only when we have redshift information in principle, but this is kind of fully data-oriented way to getting the redshift information for all the galaxies. This is probably almost impossible because it requires huge amount of time. But instead, we can choose model approached way to do this, which means we can take a kind of couple of reasonable assumptions to minimize this kind of things. So, since the JWST data became available, our group tried to obtain the infrared source count using JWST data, especially 6 millibands from 7 to the 21 micron, using Stefan Quintet's field and Shear's field data. So we reported this kind of source count results to MNRAS. And To interpret this kind of source count results, basically we need to know the galaxy distribution, at least in the local universe. So yeah, these are local luminosity function at redshift 0, usually given in terms of luminosity and density. So we adopted one of the best luminosity functions in which these kind of shapes are already decided based on the previous observation from Spitzer and Herschel and so on. So this is the first assumptions we took in this work. And for galaxy types, we try to simplify the mixture of galaxies. So in the real universe, there are so many different types of galaxies in size, mass, or shape. But in this work, we simplify the galaxy population so that there are only 5 major types in the universe. So the mixture of these population, for example, star-forming galaxies, starburst, agent type 1 and 2, and composite. The mixture of these populations are distributed in the local universe according to their luminosity functions. And next, they evolve along the redshift. So, like this, according to this equation. So this is an example, the evolution of a local 15 micron local luminosity function along the redshift. The color bar shows the redshift. So in our calculation, the redshift, so our calculation covers up to the redshift 8. And these equations are important part of this work because they are showing a kind of rules of how the luminosity functions evolve as a function of redshift and this kind of evolution parameters. So here the A, kappa, omega, these parameters are regulates how luminosity functions evolve. And then the luminosity and density in this figure can be finally converted to the observed flux density and actual number of galaxies like this. So we can obtain this kind of figure. So this is normalized the number count of galaxies as a function of observed flux density. So if we integrate over all the redshift ranges and for all the galaxy types here, we can obtain integrated number count of galaxies as a function of observed flux density. And this is our source count model. And we need to compare this model against the observed source count. So we obtain the JWST source count first and combine them with the previous source count from Spitzer, Akari, and ISO. So this comparison is kind of fitting process. So sometimes we go back to obtain some better parameters to match these models against the observed source count. So this is kind of iteration until we obtain best fit model. So yeah, we fit a model to observe the source count in the 6 millibands simultaneously. So the red open circles here are the JWST data point, and the other symbols, diamond, triangle, these are previous infrared source count, so on the brighter side. So when we obtain the best spin model, these parameters that I showed you just before, omega, kappa, are decided. So for example, in 15 micron source count, this red curve is our model, and this is integrated results from all the 5 galaxy population. And then the fainter end and the brighter end, we can see that this green red line, which is star-forming galaxies. And then, if we compare with the previous model, so this yellow-brown curve is previous model, and this is based on the previous source count from Spitzer and Akari, but it doesn't include a JWST source count. But our model includes all the data points. So this is kind of updated version with a little bit more fine tuning. So this is an updated version from the previous model. So this is our final goal, the star formation history. So from the source count, with some assumptions for luminosity functions and evolutions for 5 types of galaxies, we can obtain the new parameters. And using infrared luminosity density, we can obtain star formation rate density, which is this red curve here. So this is our model, and we compared with the previous works, like red region, this is Groupianis 2021, our comparison study, and also Madao 2014 here, and Harikane et al. 2022. So our model looks consistent with the Groupiani et al., but it shows quite a large uncertainty in the overall, in the higher redshift, there is quite large uncertainty, but overall, the size of the error bar is a little bit larger in the higher redshift. The data point from the previous works seems still not enough. I think we need more observation data in the higher redshift. And so the most important thing in this work is we actually used really fainter galaxies, a micro-Jansky level in this region. So these kind of galaxies are actually these galaxies have been a kind of prediction or imagination until we obtain the real data from the JWST observation. And then after we obtain the updated parameters, these parameters give us a new cosmic star formation history model and the source count model at the same time. So that is all from me today. Thank you very much.
Thank you. Maybe one question. It's a simple technique question. Source count means just count numbers. I wonder how the error bar, in some of the error bar are very big. How was it determined?
Which error? This one?
All of your count. Yeah,
so this is our model, and this is error region, and this is from the fitting error.
Fitting?
Yeah, fitting error.
Okay. Thank you. If you have more questions, you can ask after the sessions. Okay, thank you.